Okay, now we start with the fun stuff, and we're going to actually try and figure out how to determine the order of a rate law based on data. So let's go back to what we were doing before, and I would suggest if you could open up 11.3. Got a little excited here with the pen beforehand. Sorry, you won't have that open, but we're going to work like you know how we always do the generic AA plus BB goes to CC plus DD. Notice how we don't even care about the products because again in all of our kinetics we only care about the reactants. But I want to write the rate law for this, and again when you have multiple things that are reacting, each of those individual things can impact how fast your reaction is. So the actual rate expression, as we call it, would look like this. We'd write rate is equal to, and remember, every single equation that you have an expression for is going to have a constant k, and it's going to be based on the concentration of the first thing raised to some order, some power, times the concentration of the second thing raised to some order. We'll call that m. N. Now, again, let me point out to you here, the coefficients A and B, do you notice how they are not here? We have instead M and N. And if you're like, I don't want to do M and N, then go ahead, go like X and Y or A and B or whatever you want to. Actually, A and B would be bad because that would indicate coefficients. Scratch that. But it doesn't matter what these letters are. They just represent the orders. And in fact, the wording is actually kind of very formal. And we say that M is the order of the reaction with respect to A, and N is the order of the reaction with respect to B. The overall order, and they'll sometimes ask you, what is the overall order of the reaction? You just add up M and N together. Now, if you ever have an M or an N have a zero value, I hope you understand that whenever you take something and put it to the zero power, it's 1, right? We'd say it's zero order. If it's M or N is 1, we say the reaction's first order, and if it's 2, it's second order, and so on. If we take a look at something like this, and the overall rate was this, A with the order of the reaction with respect to A is 2, and the order of the reaction with respect to B is 1. If we add it all together, this overall reaction is third order. That's kind of makes sense. But let's now get to how do we play with this and how does this look and how do we do it live. So what we can do is and this is really a big deal, in order to figure out the rate law, you always have to have a data table to pull from. Now, I'm going to write over here excuse me. I'm going to write the function of the rate law right here. It's going to be rate is equal to K, and we have two reactants over here. Don't we have NH4 plus, and we have NO2 minus. Now, what's kind of cool about this, and I'm going to show you how to do this in your head by just doing some basic arithmetic, okay? So what we can do is we can see what the relationship is between one variable and another. So let's just say if we look between experiments 2 and 1, right? If you take a look at experiments 2 and 1, would you see that NH4 is held constant? Right? Or between 1 and 2. And if you compare 1 and 2, do you see how from between 1 and 2, the concentration of NO2 doubles? So here, the NH4 is doing nothing between experiments. So what they typically do, and just so you get an idea, like what are you talking about here? What they do is they actually run this expression. I'm going to change the color here so it doesn't get lost. They actually run this overall expression up here. They run this a bunch of different times. Sometimes they hold the concentration of NH4 constant, like they did here between experiment runs 2 and 1. Sometimes they hold the concentration of NO constant because they want to see what happens to the rate of the reaction. So would you be okay if these two things right here stay constant? That means that the only thing that's impacting the rate of the reaction, the only thing, is NO2. And if you take a look right here, in between experiments 1 and 2, the concentration of NO2, it doubles. And the rate also doubles. So if you take a look between here and here, this doubles. So when something doubles and the other thing doubles, you have first order. Now, let's look, and again, we have to hold the other thing constant in order to compare the first thing. And will you notice here that experiments 2 and 3, right, 2 and 3, do you see how NO2 minus is held constant And you see how the NH4 plus concentration, it doubles. So we have the NH4 plus concentration, it doubles. And again, if you take a look at the rate doubles. So this is a pretty gentle way of doing this here. That means that it's also first order. Now, going back to our original equation up here, that would mean this. If you're writing it out now, we'd say, well, a rate is equal to K NH4 to the 1 to the first order and NO2 minus to the first order. Often they won't even write the 1 in there. They'll just write it as NH4 times NO2 minus. Does that kind of make sense? Asking, although I know that you can't give a response. Now, what you should be aware of is that if one thing doubles and the other thing quadruples, that would be second order, right? And if something doubles and the other thing does nothing, that would be zero order. Now, obviously, it'd be good to go over in class, and we will, a few of these examples and kind of show you how this all works. But the problem is this is a really, really basic problem. What if we get into much more complex problems and they have multiple things and there's a lot more choices? And what if something isn't held constant? There's something called the method of initial rates, and that's the next video we're going to do right now. Hopefully this has been helpful. Thanks. Bye.